let's see. Let me just make sure that Ignacio can share screen. Maybe you should be co-host as well.
Yes, I did that before. I have checked it.
You did. Okay. Okay. Excellent. Okay. Well, welcome everybody for this edition of the Colloquium. So it's a distinct pleasure to have Ignacio here as our speaker today. Ignacio is has done really groundbreaking work. His work with Peter Zoller led to the possibility of ion trap quantum computing, to optical lattices, and to his work on that opened up the possibility of doing quantum simulations in that technology. So I cannot think of anybody better to talk to us about quantum simulations. In addition to all this, he's done, of course, really amazing work on theoretical condensed matter physics, with the definition of PEPs and other tensor networks. He's a much decorated physicist. He won the Wolf Prize in 2013 and the Benjamin Franklin Medal with Peter Zoller, and so real pleasure to have you here, and looking forward to your talk, Ignacio.
Okay. Okay, well, thank you very much. Thanks a lot for the introduction, and thanks for the invitation. It's my pleasure to be here and to give this talk about quantum simulation. And so first of all, I would like to, well, I know that there is a mixed audience here from physicists and computer scientists. And so I would like to apologize to both of them because, first of all, I'm using more the language of physics. So when I talk about algorithms and I talk about computational times, then you will not see this typical notation of computer scientists, but rather this kind of hand-waving notation of physicists. But I also have to apologize to physicists because in several times I'm not going to explain the physics behind that, but I'm going to talk about, how difficult it is to solve some problems in quantum simulations. Okay, in any case, I'm looking very much forward to the panel discussion afterwards, because we have also several physicists and computer scientists, and I think it will be a good mix to discuss about quantum simulations. Okay, so let me start here saying that we are living now a wonderful area. So for people who have been working on quantum computing for 25 years or longer, and there are quite a few here, then I think that the dream is coming true. So we don't have a quantum computer yet. We don't have a scalable quantum computer yet, but we have already at hand what are called analog quantum computers and NISQ quantum computers. So these are devices which don't behave in the way that we would like to behave, because they have some errors, or they are not perfect, or they are analog, but still with them, some people have been able to do things that otherwise, would seem impossible several years ago. And some of them go beyond to what we can calculate. So that's an area in which, I guess that everybody is trying now to see what can be done with these devices, with these analog quantum computers, with these mixed devices, and especially if there is any advantage in solving some problems that are, let's say, useful for society. I'm going to talk about some particular kind of problems which are very well suited for quantum computers in general, but also for analog and NISQ devices. And these are quantum many-body problems. And these are problems that appear in physics and chemistry, and they appear in many areas of physics and chemistry. So first of all, if you like to know what is the possible reactions of a molecule, or what is the geometry of a molecule in space, then you will have to solve one of these quantum many-body problems. If you're studying solid-state physics, or you're studying condensed matter physics, especially at low temperatures, then you will have to solve these quantum many-body problems. Or even if you solve high-energy problems and you're looking at the G-2 factor of ions or basic particles, then you will have to solve one many-body problem of this kind. And so these problems, even though they appear in many different areas of science, they have something in common. So typically, if we want to describe them, the first thing that we do is that we put them all of them on a lattice. So for the case of chemistry, when we take what are called orbitals and express everything in terms of these orbitals, at the end is formed like a discrete set. In the case of condensed matter physics, then this is very natural because the atoms are aligned according to a lattice. And so you want to talk about the properties of these atoms, then the lattice is already given by nature. In high energy physics, this lattice is provided just by discretizing space. And then what you do at the end is that you have some lattice in spatial dimensions, in 1, 2, 3 spatial dimensions. Typically, these are regular lattices. Even in quantum chemistry, of course, this is different. And in all these systems, what we typically do is that we know what is the Hamiltonian. The Hamiltonian is what is telling us how the different lattices interact with each other. So the typical problem in these systems is that you have a set of qubits aligned on a lattice interacting with each other according to some laws, which are given in the form of Hamiltonian. And then we would like to make predictions about these systems. We would like to predict if a chemical reaction will take place. We want to predict whether a material will be superconductor or will have magnetism or other properties. We would like to predict if the quarks would form some particles, what would be the mass of these particles, and so on. These are typical predictions. And so what we have to do in practice is that we have to solve a quantum many-body problem, and at the very end, write what is the state, the quantum state of these systems of qubits. And so at the end, when we write what is the state, it will be a linear superposition of the possible configurations, all running from all possible qubits, the state 0, all the way to all the qubits in 1. And the physical properties to the answer to the question that I posed are in the coefficients, these complex coefficients in front of them. So in other words, typically, if we want to solve any of the problems that I mentioned before, we will have to find these coefficients. And once we have the coefficients, then we can combine them in order to compute this, to make these predictions that I mentioned before. And you already see that the number of coefficients grows exponentially with the number of qubits, which in turn grows exponentially with the volume or the number of atoms that you have in your system, and so on. And so this means that if you want to solve this problem with a classical computer, at least if you do it naively and exactly, then you will have to pay a price in the memory. So you'll have to use a memory that grows exponentially with the number of qubits just to accommodate all these coefficients in your memory. And if you want to make any prediction or you want to compute anything, then you will have to do at least one computation with each of the coefficients, or also the computational time will scale exponentially with the number of qubits. So we have this double exponential in memory and exponential in time. And while in some problems there is just an exponential in time, so quantum many-body problems have this additional property that's exponential also in memory. In fact, some people have asked the question, so what happens if I only have polynomial time of memory? What happens if I have, let's say, a classical computer with limited resources? Then you can trade time for a space or for memory, and then it turns out that the computational time that grows like 2 to the n, so typically it's some poly n, so 2 to the n to the power n, things like that. So it grows very, very, very fast. So in other words, the quantum many-body problems are especially difficult for classical computers, and that's why, I mean, many years ago, people realized that, and especially Richard Feynman, and so he proposed the field of quantum simulation. So he said, well, if I want to solve a problem of n qubits, instead of storing it in a classical computer, what happens if I have n qubits themselves? And what I do is that I prepare the state of n qubits. Then I will not have to use exponential resources in memory, because I will have to, I can store the state of the qubits in the qubits themselves. And so right away, you see that the memory, if you use a quantum system, a quantum computer, then will grow linearly with n. So that's already right away some gain. And on top of that, then depending on the problem that you want to solve, so there are different kinds of problems that you're interested in, then it turns out that the computational time may run either linearly with n or exponentially with n or whatever. But you see that, I mean, already right away we have this big advantage in the memory. So that's why quantum computers are especially suited for solving quantum many-body problems, and that's the obvious application of a quantum computer, because these problems are relevant in physics, chemistry, science, and they're very difficult to solve. So what I'm going to talk about is actually algorithms, so quantum algorithms for these many-body problems. And so these quantum algorithms I will be considering typically a lattice in any dimensions. I will consider local Hamiltonians, meaning that the Hamiltonian that describe interactions in the system is the sum of terms that are only locally. So there is maybe a term that acts only in these 5 qubits here, and then another one that acts in some other qubits and some other qubits, but all of them are local. And so typically you see right away that this Hamiltonian, so the norm of this Hamiltonian, the typical values that this Hamiltonian will take will be proportional to n. So the bigger the system, then the bigger are the values of the energies that I will get. And there will be some proportionality factor typically. Okay, so I concentrate on lattices of whatever kind, qubits on the lattice, even though it could be higher dimensions. And at some point I will talk about something about higher dimensions, and Hamiltonians that are given, which are local. And this already contains many problems that are interesting in physics. And if you press me, then I will tell you that even all problems in physics are like that, because if you have non-local interactions, then the underlying theory is local, is always local. So what happens when we have non-local interaction, like you have Coulomb interactions that decay like a Power law, is that quantum electrodynamics, actually, which is local, what you do is that you simplify this Hamiltonian, and this gives rise to some effective interactions that decay, that are non-local. So what I'm saying is that only going back in the theory, you can always formulate your theory as local. So that's, in that sense, it's not a big assumption. Okay, and so I'll talk about quantum algorithms first for solving the dynamics. So you want to describe, if I start with some initial state, so what will be the physical properties of that system after some time, or 0 temperature. So if I cool this system all the way to 0 temperature, then what will be the physical properties? And then I'll talk also about finite temperature. So what happens if they're at finite temperature? And later on, so I will also talk about verification. So how the field of quantum simulation may give rise to some verification math spirit of what people in Berkeley have pioneered, of how you could check that your quantum simulator is really doing what you're asking. And so you imagine that you don't trust it and you want to make some, gain some confidence that somebody else that has a quantum simulator indeed has a quantum simulator. And at the end, I'll talk a little bit about analog versus digital. So I will talk about these advantages and disadvantages of analog versus digital. And that's a little bit controversial. So I hope that this goes directly to the panel discussion and that we can address some of these questions there as well. Okay, so I start talking about quantum algorithms, dynamics and ground states. Then I'll talk about finite temperature, then about verification. Okay, so what is a typical problem in dynamics? So again, you're giving your lattice, you're giving your qubits, and you're giving your Hamiltonian. You're also giving some initial state, which is easy to prepare with a quantum computer. So for example, you have a product state. And then you're also giving some operator, some observable. And at the end, what you would like to compute is the expectation value of this observable up to some error epsilon, and of the time of the state, which is time evolved according to your Hamiltonian. So you start with the easy to prepare state, then you would like to see what happens if you evolve it and you compute some physical property, namely some expectation value of some observable up to some error epsilon. Actually, one of the first algorithms that was developed was to solve this particular problem. This was by Seth Lloyd in 1996. And so what he did is that he found an algorithm just to do exactly that. And then he found that the computational time, and so here, when I'm talking about computational time, you may think that this is like the depth of the circuit, of the quantum circuit. So the circuit depth would scale proportionally for a local Hamiltonian, like the one that I'm treating here, with the number of qubits that you want to simulate, with the time you want to evolve, and with the inverse of the error that you are allowed to have squared. So this algorithm has been improved by a lot during the last years. And so I don't know, so typically state-of-the-art algorithms have a computational time, which is linear in n, linear in time, and logarithmic in 1 over this error. So these algorithms, if you run them with NISQ, then you have to pay a price. So this is not so user-friendly for niche devices. This is a bit more user-friendly for niche devices, but still you have to trotterize the evolution. So you have to decompose the evolution in many quantum gates. So there is a lot of overhead gates. However, you had an analog quantum simulator. So maybe, an analog quantum simulator, for the one who doesn't know, is the one in which you take another system. So you're giving this problem with a lattice and a Hamiltonian. And then you take another system that could be, for example, cold atoms in optical lattice, and then you engineer the interactions in your systems. Well, you put them on a lattice, physically on a lattice, and then you make them interact with each other according to the Hamiltonian that you want to simulate. That's what is called an analog quantum simulator. So you had a quantum analog simulator, then this problem is trivial. You just start your prepared state, and then you don't do anything, just let it evolve. And then at the end, you measure this observable, you repeat it several times, like in the other cases, and by taking the average, then you will estimate what is the expectation value. Okay, so again, the problem of computing dynamics with analog simulators, with niche devices, or with quantum computers is extremely advantageous with quantum computers. Now, if we consider another problem, that's the ground state problem, which is the following. So imagine now that I take my Hamiltonian and I compute the eigenstates and eigenvalues, so the eigenvalues and eigenvectors of this matrix. And I now want to know properties about the eigenvector corresponding to the smallest eigenvalue. So this is what we call the ground state energy, the energy of the eigenvalue. And the eigenvector is what we call the ground state. So the problem is that you're given the Hamiltonian, and you want to compute the expectation value of some observable in the ground state of this Hamiltonian, up with some error epsilon, etc., etc. And you would like to know how this grows with the size of your system, with the number of particles. And now the first thing that you notice here, it was noticed already several years ago, is that this problem is very difficult even for quantum computers. Is in the complexity class, you formulate it in terms of a decision problem. So is there a state with an energy smaller than something and up to some poly n error, then is QMA hard. So it's in the class of problems that we are believed that are even difficult for quantum computers. And so the computational time in this case will scale exponentially with the size of the system. Still, this you compare with a classical computer, which would have only polynomial memory, then still there would be an advantage with a quantum computer. However, for practical purposes, this will not be that big because you will not be able to reach big sizes of your system. Now, what about this coefficient alpha? Well, this coefficient alpha, there have been many papers that have proposed specific algorithms to compute the ground state. Let me mention one of them that we proposed some years ago. And it depends, the computational time depends on what is called the gap. So the gap is just the difference between the first eigenvalue and the lowest and the second eigenvalue. Okay, so it's the ground state or the first excited energy and the ground state energy. That's how we describe it in physics. And the computational time scale is like 2 to the power n half. So it has to be exponentially in n divided by this gap and times log 1 over epsilon. So it's already a bit puzzling. The fact that typically in classical computers, so people solve for many years ground state problems very well, even though they are difficult. But there are some algorithms that work in practice reasonably well. And however, dynamical problems in classical computers are very difficult in practice. So they're not good algorithms for that. And it turns out that now for quantum computers, it's a bit the opposite. So dynamical problems are very easy, and ground state problems, at least if you want to solve them exactly, then they are computationally difficult. Anyway, of course, classically, these problems with classical computers, ground state problems, are also computationally difficult if you don't solve them exactly, let's say. Okay, so in any case, these algorithms and many algorithms that people have proposed for solving these quantum many-body problems, and all of them scale exponentially as they should, but they are not very practical for niche devices. First of all, because of this exponential scaling, and second, because they use many ancillaries, they use many techniques, amplitude amplification, phase estimation, and so on, which is not very friendly for niche devices or analog quantum computers. So this is why There are some other algorithms that are not let's say exact. They are heuristic. That, I mean, people are trying. That some of them work well in practice. And so one of them is the adiabatic algorithm. And so that's something that it's very well known in physics, and that is very widely used actually in physics for many years. And the basic idea there is that is to take the Hamiltonian and to deform the Hamiltonian slowly. So from some Hamiltonian which is trivial to the problem Hamiltonian that you want to solve. And if you do it sufficiently slow and you start with the ground state of the trivial Hamiltonian, and if some conditions are fulfilled, then you will end up in the ground state of the problem Hamiltonian that you want to solve with your quantum computer. And once you have this ground state, then you can perform measurements and compute this observable, and therefore answer the question that I told you before. So that is what's represented here. So you start, for example, with a Hamiltonian that for some parameter S, that I call S, takes the value 0, h of 0 is a Hamiltonian, which is, it doesn't have interaction, so it's a single, what is called a single particle Hamiltonian. It's a sum of Hamiltonians acting on each of the individual qubits, and for which the ground state is just all qubits in 0. And then you start changing some parameters so that the Hamiltonian depends on S, and at the end, when S is equal to 1, then you convert it, you deform it into the final Hamiltonian. And if you look at the energy spectrum, as I draw before, like what is written here, now as a function of these parameters, so what will happen is that the ground state now will change, the first excited state will change, and as long as there is a gap always between the ground state and the excited state, then the adiabatic algorithm tells you that the state will follow adiabatically your Hamiltonian, namely, it will be at all times the ground state of the Hamiltonian. So at the end of the process, it will be the ground state of your problem Hamiltonian, whenever you do it sufficiently slow. And so that's why it's, I mean, it's a heuristic algorithm, because we, first of all, don't know if there will be a gap. Always, it's difficult to prove if there is a gap in practice. And also, we don't know the value of the gap. So maybe the gap gets exponentially small with the size of the system, with the number of qubits, and therefore the time that will take in order to be sufficiently slow maybe will be in general exponential with the size of your system. Nevertheless, people, I mean, try that, and in analog quantum simulation, actually, it's something that people do. That people prepare states just by using this adiabatic algorithm, and it turns out that in physical problems, so you take now a many-body problem that appears in physics, for which we can solve it or we can do computations, we can compute these gaps. And even if there are phase transitions, then it turns out that the gap decreases like 1 divided by n or 1 divided by n squared. So they are polynomial. And so this gives, like in practice, good algorithms to solve these problems. Now there's other...
Hi, Ignacio. Yeah. Can I just ask a very quick question? So can you help, help us understand, just in your view, what's the relative importance of finding ground states versus simulating dynamics? You know, if you had to pick, independent of the tools available, you know, if we could solve both problems, what's the relative importance of them?
Well, I would say that traditionally the ground state is more important, because there are many problems. So what happens is that in condensed matter physics and in high energy physics, so typically problems are formulated like in equilibrium. Okay, so you would like to know what is the state of matter that is interacting with a lot of environment at maybe at very low temperature and equilibrium. So when it stabilizes, and this is what we say a thermal state, and that's at 0 temperature if it's very low. So typically the dynamics in solid state physics is not so important, it's the equilibrium part. And the same in high energy physics. So people are interested now in properties of the universe, like that of particles. At the moment, the mass of the particles, which are related to the ground state and excitations. However, lately with experiments on cold atoms and some other systems and trap ions and superconducting qubits, now people are starting now looking more at the dynamics. And so I would say that the relevance of dynamical problem is growing and growing and growing. And so I would say that the traditional problems is more ground states, and problems are getting more and more relevant, the dynamical ones. but probably if you ask some other people, maybe they have a different answer. Okay, so the other heuristic algorithms are variational algorithms. These are also very, very popular. And the idea there is just to also to start with the ground state and then to take a quantum circuit or an analog quantum simulation in which there are some parameters that you can tune. So for example, you can tune some couplings or whatever. And now what you do, and this is described by some unitary operations acting on your state. And so what you do is to minimize the energy of your Hamiltonian, to minimize the expectation value of your Hamiltonian with respect to these parameters. And this may give you a good, let's say, approximation to the ground state. Again, this is heuristic. So nobody tells you that with the, let's say, family of states that you consider, you can get close to the ground state. And nobody tells you that you will even find it. No? But still, that's very nice because it's kind of very universal in the sense that even if you formulate now classical problems that are encoded in quantum Hamiltonians, then you can, apply these variational algorithms, and they are very popular. So in fact, for a while we were applying these variational algorithms to these quantum many-body problems, and so we face and we were benchmarking them with numerical method that exists for these many-body problems. So we were taking, for example, a chain. What is called a one-dimensional lattice and some Hamiltonian, and then trying to simulate how a quantum simulator would find the solution to that problem. And we did it because in one dimensions there is the MRG, there are matrix product states, there are many techniques that work very well. And in practice, what happened is that we needed an enormous number of measurements in order to get results which were comparable to the ones that you get with classical computers. And this enormous was 10 to the 15, 10 to the 16. So it was completely out of what is possible from the experimental point of view. And that's why at some point what we did is that we combined these two algorithms. So what we did is what we call variational adiabatic algorithms, in which the idea is to perform the adiabatic algorithm to find the ground state, but to try to speed it up just with some variational parameters. So in other words, what you can do is that you can split up this, S that parameterizes the Hamiltonian, and then consider, let's say, different bunches of time, so that you change the time that to go from one value of S to some other value of S. And this is a variational parameter, the time in which you run the algorithm in the different bunches. And then you optimize with respect to these basically intermediate times. Before doing that, what we saw is that actually what you could do is what people also do in numerics, is first to learn a little bit about what is the spectrum that you have. And so for that, what you could do is that you can just take your initial state, run your adiabatic algorithm, and then run the adiabatic algorithm backwards, and check if you ended up with the state 0, 0, 0, because it's something that with a quantum computer is easy to do. And then depending on the times, then you can find whether you're in the ground state or not. So there are techniques of, learning about that. Everything is heuristic, of course. And in fact, so what you can do is that, for example, to fix what is the time that it requires to reach this value of S and come back with a 90% fidelity to the state. And that's something that you can plot. So then there will be a function of t. So you can find the time that is requested in order to go back and forth up to some value of S, and then plot this time as a function of S for some prescribed fidelity. And this will give you what we call adiabatic spectroscopy. So this time, so here we take actually the derivative of this time, and then we see that it resembles very well the gap. So that's a way first of learning about what is the gap of your system. And once you know the gap of your system, the spectrum, then you can use this variational formulation of the adiabatic algorithm in order to speed up the process. And what we saw is that for this Hamiltonian, that's a typical Hamiltonian that we can solve with some of the methods with the MRG and compare. So what we saw is that in order to get some final fidelity of the state, you use the adiabatic algorithm. This is the total time. And if you use this kind of algorithms, these variational quantum algorithms, you can gain factors of 10 or something like that. So you can speed up by factors of n. This is for 53 qubits. Okay, so I think that well, I mean, it's not, let's say, terribly original. I mean, they combine these two techniques, but I think that combining them, you can do much less measurements, and also it speed up the variational algorithms. And this can, at least for this first kind of devices for solving this ground state of many body problems, this can be useful. Another thing that we did in the past and that we recovered lately is how to speed up now the adiabatic algorithms for particularly local Hamiltonians. And for a problem in which you have a promise gap. So imagine that you want to create some state, again, you want to run the adiabatic algorithm, and then you're promised that the gap that you will have is larger than a constant, let's say a constant independent of n. And this constant, then we call it delta. And then if you use the typical standard adiabatic algorithm, you see that the computational, this is the depth of your circuit, will be proportional to n and proportional to this constant to the -3 and the error to the -1. So it's always proportional to n, to the size of your system. And the reason is because in this adiabatic algorithm, when you compute the computational time and errors and everything, you have to take the norm of your Hamiltonian and or the derivatives of your Hamiltonian. And since you have n terms, you always get these factors of n. So what we found is that if your Hamiltonian is local, actually, then there is a way of getting a poly n depth, scaling in the computational time. This was done in this paper for frustration-free Hamiltonians, but we have generalized now to Hamiltonians. And just to tell you what is basically the reason is the following. So imagine that you have this Hamiltonian, which has n terms that you're going to change. What you could do is to say, well, what happens if I change one after each other? So I first change the first term, then the second term, then the third term, then the fourth term, and so on. Then you will find that the error will be n times the error because you have done n times something. And right. Then what you could say, however, if I change the first Hamiltonian, and if I have a gap, then I know that there is a Lieb-Robinson bound, and therefore things will not propagate far away. So this means that I can change simultaneously some other Hamiltonian and some other Hamiltonian, so you can do things simultaneously. In fact, you can just put the Lieb-Robinson bounds in all that, and then you see that you can do things simultaneously. So you can take, let's say, basically some pieces of your Hamiltonian and change them at the same time, then some other pieces, then some other pieces, then some other pieces. And this would be equivalent as if you do it one after each other. And if you do that, and now at the end, you have to also derive an adiabatic theorem in which the error scales exponentially down with the time. And if you combine these things, it's very easy to see that then you get this scaling. Okay, so it's an idea of just taking into account that if you have a local Hamiltonian, then you can use Lieb-Robinson bounds, and this will give you a better scaling for the adiabatic algorithm, which will be poly log n. Actually, it's a log n square or log n 1 plus epsilon, in fact, and compared to the standard algorithm. And I'll come back to that when I talk about verification. Okay, so that's, yep.
There was a question from Henry Yuen in the chat, which is, I think, rather interesting. He was asking if there's a prototypical dynamics problem that is used as a main application for quantum simulation. So is there like some fixed dynamics problem, which is what I should
Well, there are quite a few dynamical problems, and we have Immanuel Bloch after this talk in the panel. And so he has done experiments of many body localization, and and Misha Looking also has done experiments of time crystals and things like that. And I would say that these are the typical problems for dynamics. Okay, so you would like to know how long things tend to take to thermalize, or that if things somehow repeat in time, so get some periods that are not there. There are people talking about dynamical phases of matter. So these are typical problems, but I would say that that's not so established like the case of ground states, because this is, it's been working for 30, 50 or 100 years, maybe, people working on these ground states, whereas these dynamical problems are appearing now. Okay, so I'm moving on now to finite temperatures and finite energies, and I'm going to present some work that we did together with Cyril and Marie-Carmen Banyuls. And so the idea now, it's very similar to the ground state problem. And I'm going to present two different versions of that problem. So the first is, instead of giving you the ground state, I give you some energy in the middle of your spectrum or somewhere in the spectrum. And I would like to compute now also some physical properties with respect to in that state. So it's like before I gave you the ground state and I told you compute the expectation values in the ground state. Now I tell you, well, I give you something in the middle of the spectrum, compute the properties of that. And the second problem is what in physics we do more often, which is to take a thermal state. So what you would like to do is to compute the expectation values with some density operator, which is completely equivalent to compute the expectation value with respect to all possible states in the spectrum, and at the end weight them with some exponential decay. So weight is exactly the same thing. So these are the two typical problems. So the first one we would call is related to what is called the microcanonical ensemble in statistical physics, and the second one is related to what is called canonical ensemble in the statistical physics. So that's the problem. And before entering into the problem or defining it more precisely, when you notice right away that this problem is difficult. I mean, it's hard for a quantum computer, and the reason is because it contains the zero temperature state. So if I give you the E0 is the ground state, or if I give you a temperature which is 0 here, this would correspond to the problem of the ground state that I was mentioning before. And before we say that this is hard, is QMA hard. So this problem is also QMA hard. So you don't expect to have, let's say, I mean, the worst case scenario would be QMA hard. However, you could also notice that, of course, if I start increasing the energy, or if I increase the temperature, then at some point, this may get easy. And actually, if I go, for example, to infinite temperature, then the problem is completely trivial. And if I go to states of energy which are close to the middle of the spectrum, this problem is also typically trivial if you formulate it properly. So you see that there will be some energies at which the problem goes from difficult to easy, and both classically and quantum. But this position may be different from classical from quantum. So it may happen that the problem is still difficult for a classical computer, but it's easy for a quantum computer. And so I want to discuss this a little bit. And okay, so let me talk first about finite energies. And so that's the problem. And I give you some energy. And now I would like to find the physical properties, but as you see, this problem is very ill-defined if I define an energy, because first of all, the spectrum is discrete. So if I give you some energy, that probably there is not an eigenstate exactly, this energy. This is why you have to formulate it a little bit more carefully. And also you would like to scale it. So one way of doing that is to give you not the energy, but to give you what is called the energy density, namely the energy divided by the total number of particles. I told you before that for these local Hamiltonians, the energy is extensive, so it's proportional to m. So you divide by m, this is what is called the energy density. So I give you this E value. I also give you some observable. And also, I give you some interval here, delta. Because I mean, if I fix the energy, there will be no eigenstate. So I have to fix some width here, delta. And so the goal here is to compute the expectation value of the observables in a state that has this as a mean energy, and that has a variance, which is this delta square. So there's a square here, with some prescribed precision and giving the variance delta. So I fix this variance. I fix this small e, and I fix the observable, and then you would like to see what is the computational time, how this scales with n, epsilon, and delta. Okay, you can formulate it in different ways. You can also take, for example, as a family of states that goes with n, and then you would like to compute with these families and things like that, but that's a way of formulating. And okay, so actually this problem is relevant in physics, so people are trying to compute properties in the what is called microcanonical ensemble in the middle of the spectrum. And for physically relevant problems, then you will have to scale this delta as 1 over n. Okay, that's just keep it in mind. Maybe it doesn't matter so much why this is like that, but that's the goal. So to scale the problem, to make it bigger, and then we will consider what happens if delta is like 1 over n, and see how classical methods compare to quantum methods. Okay, so that's something that so people have been actually trying to solve these problems with tensor networks, and in particular, we have been trying to do that, and then we saw that that's very difficult. And so actually, the computational time with tensor networks is case like the exponential of 1 over delta, or the exponential in the size of your system. And the reason is that when you're trying to get something which is very sharp in energy, then you're growing, the entanglement grows a lot. And so you want to describe it in terms of tensor networks, then you need a very big bond dimension. And that's the bond dimension is case exponentially with 1 over the delta. So, okay, so this means that at least the classical algorithms that are used for that in 1 dimensions actually require an exponential time if we require the delta scales like 1 over n that I told you before. Okay, so now we're going to consider quantum algorithms, but now in arbitrary dimensions. And so the idea for the algorithm, and so I'll comment each of the points later on. So first of all is, okay, so the first thing that you can do is just prepare a state which has this expectation value of the energy. That was one of the conditions. And let's imagine that there is a state like that, which has this expectation value of the energy. However, typically it will have a much bigger width. So for example, if it's a product state, then it's very easy to show that the product state for local Hamiltonians, you compute what is the energy, then it has a variance that scales like square root of n. Okay, so it would be a huge sigma, would be square root of n, not 1 divided by n, but the square root of n, so it's very big. So when you have the state, then what you can do is to filter and to make it thinner and thinner and thinner. So that's the second part. The second part is just apply some operators, and I'll tell you what you can do in order to make it just of the width that you're asked, this delta. And the third ingredient of this algorithm is that actually you don't have to do that in practice. So what you can do is what is called time series for that. And this means that you use your quantum computer to compute many quantities, which at the end, it's equivalent as if you would have created the state and done the measurement. So let me explain this with a little bit more detail. So the first thing, take a state that is easy to prepare. Well, this is a restriction, because this means that you should be able to prepare with your quantum computer states of this energy. And this is a restriction. And of course, I mean, there must be a restriction because, as I mentioned before, I mean, this in general is a QMA hard problem. So you cannot go beyond that. In fact, in practice, you can take with product states, and you can show that you can get some values of E that you can reach, a small e, so these intensive values. Now what you can do is to take blocks, so not product state of qubits, but block qubits, and take product states of blocks and grow the blocks, and then you will be going down in energy. Of course, then the preparation and everything will get more difficult, and so that's something that you have to evaluate, so how far you can get with that. But in any case, so that's something that gives you a restriction to prepare the state. The second, the filter, you have the state that you prepare, this P, then you like to apply a Gaussian filter. And so this Gaussian filter is this a Gaussian operator, which has a width delta in the Hamiltonian. And you see, if you apply this operator, what it will do will be exactly that, will filter it. And however, this operator is non-unitary. So in practice, you will not be able to apply it. And so what you can do is to expand it in series, time series. And then at the end, when you want to compute an expectation value of this observable, that was the goal at the end, then what you can do is replace in these formulas, this psi with this series, and you see that at the end, this is a formula which contains expectation values of these quantities and these quantities. So at the end, what you can do, what you have to do in your quantum computer is to prepare your state P and to measure these kind of log-Schmidt echoes. This is this quantity. So what is the amplitude that you start with the state, evolve for a certain time, do you go back to the initial state? And if you do that, then you can replace it in this formula, and then you will be able to compute this problem. So now you can check, so what is the computational time of that in a quantum computer, and you can, I mean, show that it's polynomial in n in 1 over delta and 1 over epsilon, and therefore this should efficiently allow you to compute the properties taking this delta 1 over n, no, beyond what we know with classical algorithms. Of course, until some energy, which is the one that corresponds to the state that you can efficiently prepare. Okay, so this was the first algorithm. This is for zero temperature. Now let me go to the finite temperature. They will be very similar to that. And so maybe I go a little bit fast because I want to talk a little bit about the verification here. So the problem is the same as before. You're giving some temperature and they would like to compute the expectation value of some observable at the given temperature. So for this density operator, and you would like to know how this grows with the size of your system. And so now what happens is that there is a classical algorithm that does it. And so I wanted to explain that a little bit on detail, but I don't have time. So this is quantum Monte Carlo. It's a classical algorithm that basically expresses the expectation value in terms of some expectation, some average with respect to some probability distribution. So basically what you have to do is to sample according to this probability distribution and then compute these expectation values. The problem in quantum Monte Carlo is that this probability distribution, in order to compute it and be able to sample, then you have to solve a many-body problem. And so that's hard in general. So what happens is that there are some instances for which it is possible to re-express this many-body problem in some particular way and doing this sampling. And then this is when quantum Monte Carlo works very well. However, in many problems, this is not possible. It's not possible to use this trick, and therefore you cannot compute this easily. And therefore, these are the problems where quantum Monte Carlo has the sign problem. And when it has the sign problem, then quantum Monte Carlo takes an exponential time with the size of your system in solving these problems. Otherwise, so typically, let's say it's a heuristic algorithm, in any case, takes a polynomial time. Now, so how can a quantum computer help? Well, it turns out that you can re-express also this expectation value, and you can do this trace in terms of states that are easy to prepare. And then it turns out that at the end, what you can do is that if you can re-express also as some expectation value, you're able to sample. But now the probabilities that you have to compute in order to sample can be computed with a quantum computer. It depends on the quantities that I told you before. So again, this algorithm, gets around, circumvents the sign problem in quantum Monte Carlo. It uses quantum Monte Carlo, and the quantum computer is a subroutine which computes this probability in such a way that you can sample. And of course, there are some requirements, is that it cannot go to, you have to be able to prepare states at the corresponding end, at the energy corresponding to this temperature and so on. I mean, there are some details there, but still I think that is quite interesting that you can, for some cases, get rid of the sign problem in quantum Monte Carlo just by using the quantum computer as a subroutine. Okay, so I move to the last part of my talk, then it's about verification. That's some work in progress. And so the idea is to show how quantum simulation can be used in verification. And so for that, let me introduce very briefly PEPs. I guess that you had some other talks on PEPs. So you have a many-body system and a lattice. Then there are families of states called tensor networks, which sometimes approximate well these many-body states. They are based on some tensors. They are constructed out of some tensors that are contracted according to some indices to give this many-body state. So they have this physical index and the auxiliary indices, and they are contracted according to the auxiliary indices in order to give the many-body state. What is important for my talk is that in any dimensions, if you talk about these PEPs, there is a subclass of them which are called injective, in which this map is invertible, meaning that if you consider this tensor as a map between these auxiliary indices, so these black lines and the red line is a map between the black and the red. If this map is invertible, then you call injective. And it turns out, actually, this is a generic property. So it can be shown that by blocking log D, where D is the bond dimension, then generically all PEPs becomes injective. So it's not a very big restriction. So I'm going to consider now injective PEPs. And so what happens with these injective PEPs is that they are the ground states, they are unique ground states or local frustration-free Hamiltonians. Okay, so you give me one of these many-body state, then there is a Hamiltonian for which this will be the ground state, and this will be the unique ground state. And so the idea is first to build an algorithm that would prepare that state. Okay, so what we want to use is the Adiabatic algorithm that I was presented before to start with a trivial state, deform the parent Hamiltonian, and to end up with the parent Hamiltonian corresponding to this state. Of course, for this algorithm to work, you require that there is a gap. And so what you can do is now, well, if there is a gap, so you can prove that there is a gap for the whole path, then the time, the computational time to build that will be this polylog n, basically, that I mentioned before, because it's a local Hamiltonian. But now what we did is that we found a way of finding lower bounds to gaps and non-trivial lower bounds of gaps of these parent Hamiltonians, and expressed as a series of n SDP problems, semi-definite problems. So in fact, I mean, we can show that there is a range of, let's say, of Hamiltonians around some ball, around the original Hamiltonian, the trivial Hamiltonian, for which you can prove that there is a gap. And therefore, then there is a sequence, there is a series of these PEPs that you could efficiently prepare. That's the first part. And the idea there to prove this and to translate it is to prove this property in the Hamiltonian. This proves that there is a gap, and then we decompose in n SDP problems, local SDP problems that can be efficiently solved. Now, the second part is something for a property of PEPs that I didn't know, but that's quite surprising, at least for me, is that actually, if you give me injective PEPs, I can find a set of observables, and they can compute the expectation values of these observables. And this set of observables is a complete set. So it's usually informational complete. So you could do the quantum tomography with them. Okay, so you give me a PEPs, and then I can efficiently find some set of observables R alpha and S alpha, such that the expectation value for some of them is 1, for some of them is 0. These are just written in terms of the tensors, and they form a complete set. So each of them, of course, would be, let's say you write it in the Pauli basis, would be very complex in the Pauli basis. Some of them will be simple in the Pauli basis, but in the general one would be complex in this Pauli basis. And they form a complete set. And the idea there, well, I will skip that. So, I mean, it's a property of these injective PEPs that you can use in order to compute that. And so this invites you to propose a verification method in which, in the standard scenario, there is a verifier that's a prover. The prover has a quantum simulator, and the verifier wants to make sure that the prover has a quantum simulator, and that's really quantum. And so can ask questions. The prover can use, if he has the quantum simulator to answer these questions. And then the verifier had to make sure that indeed the prover has a quantum simulator, cannot do it like with a classical computer. And so the idea, just using the properties that I told you before, is first, so the verifier sends the instructions to prepare the state, okay, sends this Hamiltonian and calls the Hamiltonian or the adiabatic or the circuit behind that, so that the prover can prepare the state. And then the verifier asks Pauli operators for all qubits and measure this Pauli operator on that qubit, that Pauli operator, and repeat it many times and with many Pauli operators. And the prover, what has to do is the sample, so return the samples. And once the verifier has the sample for enough number of, let's say, products of Pauli operators, then he can check these observables that I mentioned before. Exactly, so he can make sure that these observables, for which he knows, because he's a PEP, that they have to have expectation value 0 or 1, they can check some of them and check that. And so now, okay, so what can one say about security about that? Well, the first thing is that, okay, so sampling from PEPs is hard, actually it's sharply hard, even if you have some errors. And so in general, so if we would give a PEPs and say sample from these PEPs, then the prover, I mean, should have a hard time to sample that. However, we have a specific set of PEPs because these are the ones for which we can compute the gap. But these ones include the cluster state. And therefore, if the verifier would ask in an iterative way to measure some cluster state corresponding to some quantum circuit, then in order to sample correctly, then the prover should be able to have a quantum computer, to the power of BQP, because it has a cluster state which can use one-way quantum computation. However, now for that, this, of course, if he wants to do the whole tomography, so to take random observables for which you can compute, then many of them will require, I mean, if you write in terms of value operators, have an exponential number of operators. And then to check that, at the end, the verification would take an exponential time. So still the verifier could make sure that the prover has a quantum simulator, but it will take an exponential time to simulate that. So this is, if he wants to use a polynomial time, then he wants to take a subset of these samples of these observables that I mentioned before, for which you can do this computation in polynomial time. And of course, I mean, this reduces the complexity, and this makes it probably more, well, that doesn't relate it to complexity, to some complexity class, makes it weaker. But I mean, the point that we have is that if you have an algorithm that can spoof and compute these expectation values efficiently, even these ones that can have a polynomial number of Pauli terms, then what you could use is to build a classical algorithm to compute expectation values with PEPs. Because if I have a PEP and is injective, I can compute these expectation values. And now, if you have an algorithm to fixing this set of expectation values, sampling according to the Pauli basis, then you could sample, and then I can use that to compute the expectation values that I want from these PEPs. So I think that in any case, it's an interesting problem, because either it gives you something which is secure, and if it's not secure, it will give rise to some classical algorithm to computing expectation values of PEPs. And yeah, so I think that my time is up. So very briefly, I wanted to mention something about analog versus digital quantum computers, and I will just mention one, I would say just one transparencies. So what are advantages and disadvantages from analog versus digital quantum computers? Okay, so analog, first of all, they are not universal. So typically you can only implement certain kind of Hamiltonians with them, but not a universal circuit. For analog quantum computers, typically there is nothing like error correction, so they are not scalable in terms of error corrections. However, they are easy to build. Actually, I mean, Emmanuel has quantum simulators already running for quite a few years, with having, I mean, thousands or hundreds of qubits. Now, what about the errors? And that's this a bit more controversial part. So it turns out that in the Hamiltonian, so you want to have an analog quantum simulator, then in practice there will be some errors. So this will mean that the Hamiltonian that you want to that you have in practice will not be the one that you want to simulate, but there would be some small terms, but actually there would be n of them, because for each of the sites there would be one of these errors. So this means that the error in your Hamiltonian is extensive, or the norm of the error would be much larger than one when n is large. And so one would say that if I have an error that is so large, then I will not be able to observe anything with that. However, it turns out that in practice, in many of these experiments, what they are interested is in observables that are intensive. So they are interested in something like the magnetization per particle, because you want to compute some averages per particle. And it turns out that these errors that they get are related to this epsilon, not the epsilon times n. And so you would say, and so why, so where can this be used? And is this true what you're saying? Well, I mean, let me tell you something that is an evidence, because this is an experiment carried out by Emanuel Bloch many years ago, in which he was doing kind of quantum simulation. So he had to simulate the Bohr-Hubbard model, that's a Hamiltonian, this would be this Hamiltonian. In practice, he had some errors, and these errors were extensive. So this was of the order of 5 or 10%, 0.1 or something like that. And at the end, the physical question, which is that one wants to address, is whether if you change the parameters of your Hamiltonian, there is a phase transition. Namely, that the properties change abruptly. And then this is what he observed directly just by looking at the experiment, whatever this is, then you see that if you change the parameters, there's an obvious phase transition. And so even though at the end, the Hamiltonian is not perfect, has extensive errors, he was able to answer the physical question, which is relevant, in a very efficient way. And so that's why, of course, this is from complexity theory, that's not formulated as a complexity theory. But at the end, you want to solve a problem. Is there a phase transition? Is there some order parameter? Is this physical property? And for these quantum simulators, these analog quantum simulators, then even if there are errors, then you can still be able to solve one of these problems. And I think that with that, I will finish my talk just by going to the to the acknowledge. So just mentioning the people who were involved in the variational algorithm is Benjamin and Jordi, and the speed up Adiabatic, Jimin, Andras, and Norbert. Finite temperature, Mari Carmen and Siriu Lu, and verification was Fabio, Esther, Norbert, and Jordi. And many of the things that I have talked about here, I discussed with Misha Lukin, who is doing some experiments on adiabatic and many other things. So I have a lot of collaborations with him. So thank you for your attention.
Great, thank you. Thanks, Ignacio.
There were a couple questions maybe that we should take first. Now is a good time. So Dan Stamper-Kern had a great question of, can one use the advantage of a quantum computer to conduct time-dependent calculations in imaginary time in order to also find the ground state efficiently? Actually
not. So there have been algorithms that do that, and they're exponential. I mean, they grow. The computational time grows exponentially. So the fact that if you take imaginary time, then it's not a unitary operation, and the thing that you can do with your quantum computer is unitary, gives you this overhead that is exponential.
And there's one other question by Shiva Prasad Omanakuttan, which was, you mentioned the role of temperature to the hardness of simulating a quantum system classically, but what about the role of decoherence in the hardness of simulating classically?
Well, you have dynamics with decoherence, then it can be efficiently simulated. That's something that was shown many years ago. And the other thing is that if, because you have decoherence, then probably you cannot get the right result in quantum simulation. So even you have decoherence, you will have entropy. You want to find what is the ground state of a system, then you will never be able to find the ground state. You will find something that may be close in some sense, but it will not be. So depending. So simulating decoherence is efficient. However, working against decoherence, it's bad. However, as I mentioned before, at the end, for an analog simulation, for some of the properties that you're interested in physics, these are intensive quantities, if the amount of decoherence is still, reasonable, then you can still be able to answer those questions.
Great. This last question just showed up in the chat. David Ding asks, given the current state of experimental quantum computers, what is the outlook for realizing your algorithms?
Well, we are collaborating now with some experimentalists and doing that. And so one of the questions is how the errors will affect us. And so that's something that we are really looking at. So we did some simulation with errors in the paper that we wrote, and we were very optimistic. But now we have to, when we're talking, we're talking really about experiments that will be done in the lab with superconducting qubits, in fact. And this is when you start thinking about experiments, that it gets hard. Okay, so let's see.
Great. I think those are all the questions I saw in the chat. If I missed any, please unmute and ask right now, I guess.
Great. So maybe we should let's thank Ignacio again for this for a wonderful talk, and we can now move on to the panel. So